Bismillah ar-Rahman ar-Rahim. This video is about the elementary renewal theorem. So we have a renewal process. So we have, this is t equals 0. And here we, at time t equals 0, the number of events or arrivals is equal to 0. Then we start getting arrivals. The inter-arrival times, u1, u2, u3, and so on, they are an IID sequence of non-negative random variables. Here we will assume also that each one of them has a finite first moment expectation of u. The number of arrivals is nt, and this is the number of arrivals on the interval from 0 to t, t included. The expected value of n of t is the renewal function small m of t. The elementary renewal theorem says that if we take m of t over t and we try to take its limit as t tends to infinity, the limit does exist and is exactly equal to 1 over the expected value of u, the first moment of the inter-arrival time. Now, we are dividing m of t by t, and of course, t grows without bound in the limit. So it seems like if this statement is to be true, like m of t in the limit as t tends to infinity cannot be finite. And this is true. So now we will start the investigation by showing that m of t itself tends to infinity as t tends to infinity. And actually we will make the statement first for n of t itself. So n of t converges almost surely to infinity as t tends to infinity. And the meaning of this statement is that the limit as t tends to infinity of the probability that n of t is greater than or equal to n, this is given or fixed, that this limit is equal to 1. Why is this the case? Now, what is the probability that limit as t tends to infinity of n of t? So this is an investigation of the total number of arrivals or events. What is the probability that this is a finite number? To end up with a finite number of arrivals or points, so we keep getting those arrivals or points on the non-negative real line, we end up with a finite number of arrivals if there is an inter-arrival time ui that is infinite. In that case, the arrivals will stop here and we end up with a finite number of arrivals. So this probability is equal to the probability that there exists an I such that the ith inter-arrival time is infinity. This is the event that is equivalent to the overall number of arrivals or points being finite. What is this probability? It's a union. So we can use the union bound and upper bound this probability by the sum of the probabilities. We are using inter-arrival times that are non-defective random variables. In fact, by assumption here, they have even a finite first moment. So all those probabilities are equal to 0. So this event has a probability of 0. And this is what it means when we say that n of t converges with probability 1 or almost surely to infinity as t tends to infinity. Or we can express this using this limit statement, that the probability that n of t is greater than or equal to some given number, this probability tends to 1 as t tends to infinity. Now, this limit statement means that by choosing t large enough, we can make this probability as close to 1 as we wish. So for every epsilon greater than 0, there exists a t tilde such that for every t greater than or equal to t tilde, we have the probability that n of t is greater than or equal to n. This probability is greater than 1 minus epsilon. So as a special case, there exists large enough t tilde such that for every t greater than or equal to t tilde, the probability that n of t is greater than or equal to n is greater than 1/2. This is true for any positive epsilon. We can just put epsilon equal to 1/2. We can choose a t that is large enough, okay, and we can make this probability above 1/2. So this is n of t itself. What about its first moment? What about small m of t? So small m of t is the first moment or the expectation of n of t. This is a non-negative integer valued random variable. So it has this formula for its first moment. We can sum k from 1 to infinity, and then we have the probability that n of t is greater than or equal to k. The terms in the sum are non-negative, and so we can lower bound the sum by truncating it. So we will go from k equal 1 to gamma, and then we have here the probability that n of t is greater than or equal to k. Note that those probabilities are non-increasing. The probability that n of t is greater than or equal to 1. This probability is greater than or equal to the probability that n of t is greater than or equal to 2, and so on. So this means that we can do a further step of lower bounding. This probability here is greater than or equal to. We can replace those probabilities by their smallest. And their smallest is when k is equal to this gamma here. So this is the probability that n of t is greater than or equal to gamma, and then the number of terms in the sum is gamma. So again, we can lower bound this summation by taking the smallest term, which is the probability that n of t is greater than or equal to the highest value of k, which is gamma, and then we multiply by the number of terms, which is gamma. But now, if we choose t that is large enough, then by our argument from here, we can make all the probabilities above 1/2. So this is greater than 1/2 gamma. And we can choose this gamma to be anything, right? So the idea is that m of t is lower bounded by 1/2 gamma. Since we can make gamma arbitrarily large, then m of t tends to infinity as t tends to infinity. Okay, so again, we have m of t is for sufficiently large t, this m of t is greater than any given threshold. Okay, so this is the definition of tending to infinity. So for every let's say here, like to make it more formal, let's say that we will set gamma, small gamma, to be equal to the ceiling of, or double the ceiling of big gamma. Okay, so it's just a number. And so gamma over 2 is basically the ceiling of gamma, which is some real number, and this ceiling is greater than or equal to gamma. Okay, so for every gamma that is a positive real number, there exists some t tilde such that for every t greater than or equal to t tilde, what do we have? We have m of t is greater than or equal to gamma. So no matter, so choose this gamma, no matter how large it is, it can be huge, still we can find a large enough value of t such that for this value and for higher values, m of t is greater than or equal to this arbitrarily large value. And so this is exactly the definition of m of t tending to infinity as t tends to infinity. So if you think about the quantity m of t over t that appears in the elementary renewal theorem, it is like an infinity over infinity situation. Basically, the numerator and denominator, both of them grow without bound as t tends to infinity. But we need more. We need to show that actually this limit exists and it is equal to this value, the reciprocal of the first moment of the interarrival times. What can be our starting point? Our starting point will be this inequality, which is very important. T greater than or equal to big T n of t less than big T n of t plus 1. What is this? T of n is the sum k from 1 to n of the interarrival times. So Tn is the time of the nth arrival measured from t equals 0, the time of the nth event or arrival. So what we are saying here is that big T with a subscript big N of t is less than or equal to t is greater than big T, and then here we increase this subscript by 1. N of t is a random variable, okay? And so this may appear difficult to understand. Imagine that N of t is some given value. So for example, if N of t is equal to 7, it can be equal to any value. This means that t is greater than or equal to t sub 7. So that's the time of the 7th arrival, and is less than t of 8. Does this inequality make sense? Yes. It tells you that you visited the renewal process, you inspected the system at time t. You discover that n of t is equal to 7. So the number of events or arrivals from 0 to t is equal to 7. what does this imply? It means that the seventh arrival must have occurred before t. Because if T7, if the seventh arrival happens after T, then the count at T will not reach 7. It will be something strictly less than 7. So the fact that n of t is equal to 7 means that the seventh arrival, so this is the sum u1 plus u2 all the way to u7, this number must be less than or equal to t, because n of t is 7. But also, it must be the case that small t is strictly less than t sub 8. So the eighth arrival must happen somewhere here, because if the eighth arrival occurs before t, then the number of arrivals will be 8 or more. So because n of t is exactly equal to 7, then t must be greater than or equal to t7 and be strictly less than 8. And why do we have this inequality here and this inequality there? This is from the definition of n of t itself. N of t is a count of the number of arrivals from 0 to t, t included. So if an arrival occurs at t and we inspect the system at t, we count this arrival. So this is a very important inequality here. And what we can do is to prove the elementary renewal theorem is to take expectation of both sides. Okay, specifically, we will focus on this part, that t is strictly less than t of big N of small t plus 1. Now we need t, so expectation of both sides. And so t is a constant, so that's t less than, and then we need the expectation of this interarrival time. Now, this interarrival time it's not a straightforward expectation. Let's actually express this time here, the time of arrival n of t plus 1, in terms of the interarrival times. So this is the expectation. And here we do a summation, k from 1 to the index here, n of t plus 1, u of k. This expectation is very straightforward if the number of terms in the sum is a given or is a fixed number. So basically the expectation will be the number of terms times expectation of u, the first moment of the interarrival time. So the challenge here is that the number of terms is n of t plus 1, and this itself is a random variable. Okay, so here we have a random number of terms. And definitely there is a relation between, or dependence between, n of t and the interarrival times. The interarrival times specify what n of t will be at a specific instant of time small t. So how can we do this expectation? So here the way to go is to employ Wald's identity. So what is this? We have the following result, that the expected value of this k from 1, let's say, to v, xk, is equal to the expectation of x1, expectation of v. Okay, so here we are summing random variables. So what should these random variables be? So here x1, x2, d random variables with a finite first moment. Do we have this in our problem? Yes, because by definition, in a renewal process, the inter-arrival times are IID. And in addition, we are also assuming that the inter-arrival time has a finite first moment. So that's okay. Also, to apply Wald's identity, we need this V here. Okay, so it's random. So this is here a positive or generally non-negative integer valued random variable, okay, with a finite first moment, with a finite first moment. We will use the first moment of V here, okay, but it must be, okay, V is a stopping time with respect to the sequence x1, x2, and so on. So we can actually do this expectation, and the result is this nice result here. Even if V is a random variable that depends on the x's, so long as V is a stopping time with respect to those random variables in the sequence. What does it mean that V is a stopping time? V is a stopping time with respect to x1, x2, x3, and so on, if the event V equals, say, tau is independent of x of tau plus 1, x of tau plus 2, x of tau plus 3, and so forth. So V can depend on the sequence, but it should obey this, that V is equal to tau does not depend on, so if we here have tau, this event does not depend on x of tau plus 1, tau plus 2, tau plus 3, and so on. Okay. Can V depend on x1, x2 all the way to x of tau? Yes. It is okay. To use Wald's identity to evaluate our expectation, we need to show that the number of terms in this summation, big N of t plus 1, is indeed a stopping time with respect to the sequence of inter-arrival times. So if we verify this, okay, so if we can use Wald's identity, then this will be the expected value of u, the expected value of the number of terms in the sum, which is n of t plus 1. And now this is expected u. The expectation of n of t by definition is the renewal function, which is the topic in which is basically what we are interested in here. So expectation big N of t is a small m of t plus 1. The u's are IID, and this is required in Wald's identity. That's fine. Now the challenge is to show that big N of t plus 1 is indeed a stopping time with respect to the sequence of interarrivals. So now we do check that N of t plus 1 is a stopping time. And stopping time is a random variable, but it is defined with respect to some given sequence. So here, the sequence of interest will be the sequence of the interarrival times. So here is the check. N of t plus 1 is equal to tau. What use should we know to fully specify this event? That is, no, it is true or false. Let's see. So N of t plus 1 is equal to tau. Why N of t plus 1? Because this is a number of terms in the random sum. So N of t plus 1 is equal to tau. It means that N of t is equal to tau minus 1. Now, what are the U's that we need to know to examine this event here and know that it is true or it is false? So here is the claim. If we know U1, U2, all the way to U tau, then N of t is equal to tau minus 1 is true if and only if t is between U1 plus U2 plus U tau minus 1 and is strictly less than U1 plus U2 plus U tau, right? Now, if we know that N of t is equal to tau minus 1, then in this case, the number of arrivals at time instant t is exactly tau minus 1. So the first tau minus 1 arrivals must have occurred at a time less than or equal to t. Otherwise, the number of arrivals will be less than tau minus 1. But at the same time, the time of the tau's arrival, so this is big T of tau, this event here, event number tau, must happen later in time, later than small t. Because if it happens earlier, then N of t will be tau or more. So from the sequence of interarrival times, if we know U1, U2, U tau minus 1 and U tau, we are able to completely specify whether this event is true or false. N of t equals tau minus 1 is independent of U of tau plus 1, U of tau plus 2, U of tau plus 3, and so on. And this is exactly the definition of a stopping time with respect to a sequence. Okay. We have this inequality here, and we start by taking the expectation of both sides. Expected value of small t is a small t. Expected value of this thing, now this is like a monster. Write it down in terms of the interarrival times. This is the time of occurrence of event big N of t plus 1. So it is the sum of the first nt plus 1 interarrival times. The problem with this expectation is that the number of arrivals at time t N of t, this is the count of all arrivals from 0 to t, this itself is a random variable. So the number of terms in the sum is random. Now, we have Wald's identity, which tells us that this expectation here sometimes can easily be written as the expected value of one of those guys. So here it is expected value of u times the expected value of the number of terms, expected value of n of t plus 1, which is small m of t plus 1. But we need some conditions. We need those guys to be IID perfect, because this is exactly how renewal processes are defined. But we also need n of t plus 1, or the number of terms in the random sum, to be a stopping time with respect to this IID sequence. So we spent some time to verify that, yes, by the definition of stopping time, n of t plus 1 is indeed a stopping time. So Wald's identity can be applied, and now we have t less than big T n of t plus 1. Then we take expectation, and this means that t is less than expectation of u, expectation of nt plus 1, and this is expectation of u, and then mt plus 1, like this. Okay. Now divide both sides. Okay, so divide both sides by t expected value of u. So 1 over expected value of u is less than m of t over t plus 1 over t. Okay. Now, we don't know whether the limit of m of t over t exists. We are doing this investigation. And so at this step, what we will do is that we will take the limit infimum of both sides. So take liminf as t tends to infinity of both sides. Now, the left-hand side is nice. It's just the number, 1 over the expected value of u. So the limit is the number itself. We are taking limits, so we'll change this from a strict inequality to an inequality with the possibility of equality. Then we have the limit infimum of this summation here. Note that we have a quantity here. We are still investigating it, but then 1 over t will go to 0 as t tends to infinity. So this limit, 1 over t tends to infinity equal to 0, this limit we are sure of. It exists. The limit of 1 over t as t tends to infinity exists and is equal to 0. So because of this, the limit infimum of this sum, because we have here this has a particular limit which is 0, then the limit infimum of the right-hand side is limit infimum of m of t over t plus limit infimum t tends to infinity 1 over t. And if the limit exists, then limit infimum is equal to limit supremum is equal to the limit. So this is equal to limit t tends to infinity 1 over t, which is 0. So now we have our first inequality. Our first inequality is that 1 over the expected value of u is less than or equal to limit infimum t tends to infinity of m of t over t. Now, basically, if we can reach this, then what is the strategy now? the strategy is clear. Limit infimum is always less than or equal to limit supremum. Okay, so limit infimum, liminf, t tends to infinity, m of t over t is less than or equal to limit supremum as t tends to infinity, m of t equal to t. If we can show that the limit supremum is less than or equal to 1 over the expected value of u, and we have already shown that this is superior to 1 over the expected value of u. So if we can achieve this part here, then we are done. Because in this case, we have a chain of inequalities. We start by 1 over expected value of u, and it's also the guy here. So every term here is equal. So limit infimum is equal to limit supremum is equal to 1 over the expected value of u. Okay, so again, because of this property that limit infimum is less than or equal to limit supremum, if we can show that limit supremum of m of t over t as t tends to infinity is less than or equal to 1 over the expected value of u, then we are done. And we will have a proof for the elementary renewal theorem. But we need an inequality now, and it's like in this direction. How can we do something like this? So here is the trick. We will define another renewal process. Consider the renewal process with interarrival time. And to distinguish this process from our process, the original one, let's say that this interarrival time is u tilde, and u tilde, so they use, so u tilde 1, u tilde 2, and so on, they are IID, and they are defined in terms of the use. U tilde is u if u is less than or equal to some given big M, and u tilde is M if u exceeds M. So in our new renewal process, we have an interarrival time that is basically the same as u if u is less than or equal to M. But if u exceeds M, u tilde will take the value big M. So this is 0. Suppose this axis is for the original renewal process. So suppose that, you know, u1 is here, u2 is here, u3 is here, u4 is here, u5 is here. Okay, so this is u1, this is u2, this is u3, this is u4, this is u5, you know, then there is u6, and so on. Now the modified process, suppose that u1, u2, u3 are less than or equal to m. M is a given number, okay, it's given. And suppose that it is chosen such that in this particular situation, u1 is less than or equal to big M. Then u1 tilde is equal to u1. u2 less than or equal to m. Then u2 tilde is the same as u, is exactly equal to u2. Then u3 is less than or equal to big M. Then u3 tilde is equal to u3. No problem. So in the modified renewal process, those arrival times will be sustained. But now, suppose that u4 is greater than M. What we will do is that u4 tilde will be M itself. Okay. So what we will do is that, suppose that we'll take this guy here, and this will be u4 tilde, and this will be M, or this is M, because M is specified. Now, u5 is less than or equal to m, so u5 tilde is equal to u5. Suppose that u6 is huge, okay? So this is u6. Now, according to how we define the modified renewal process, if u exceeds the given big M, then u tilde will be equal to M. So we'll have, again, this will be moved here, and this will be u6 tilde, and this is M, and so on and so forth. So we have a modified renewal process derived from the original one, such that the interarrival time of the new or the modified renewal process is the old interarrival time. So u tilde k is uk so long as uk is less than or equal to m. But if uk exceeds m, then u tilde takes the value of m. And this is an illustration of what is going on in this modified renewal process. Okay. The claim is that in the new process, what do we have in the new process? So here is the claim. T tilde of n tilde t plus 1. So this is the time of arrival or event n tilde of t plus 1 in the modified process. So the claim is that, so we know that this is greater than t. But now this inequality is not useful to us now. We have already used it to get this result here about the limit infimum. But now we need another inequality, and this is that this arrival time, t tilde n tilde of t plus 1, is less than or equal to t plus big M. T plus big M. Okay. And the reason is that we are bounding the interarrival time by using our modified renewal process to obey this rule here. Basically, the maximum possible interarrival time is big M. So if we investigate the system at t, and we investigate the system at t plus big M, between these two, there must be this time of arrival. Okay, so let's put here the remaining part of the inequality. So this is the inequality for the modified process, and it is, we had a similar one for the original process. It's not, we talked about it earlier. Now what we can say is that this arrival time is less than or equal to t plus big M, because our modified renewal process is designed in such a way that the maximum possible separation between two arrivals or two events is equal to big M. So this is basically the trick. Now we will focus on this part and take expectation. So we'll have the expectation of this, and so this is a summation k from 1 to n tilde t plus 1, and then the modified interarrival times less than or equal to. On the right hand side we have constants, so the expectation is t plus m. Now we have verified that this n tilde t plus 1, generally n of t plus 1, this is a stopping time with respect to the interarrival IID sequence. So we can apply Wald's identity, and this is expectation of u tilde. And then we have expectation of n tilde t plus 1, t plus m. And so this is expectation u tilde m tilde t plus 1 less than or equal t plus m, divide both sides, by t expected value of u tilde, m tilde t over t plus 1 over t is less than or equal to 1 plus m over t. So take limsup t tends to infinity of both sides for the left-hand side. It is like the story above. Basically, we have the limsup of a sum, but it is equal to limsup t tends to infinity m tilde of t over t plus limsup as t tends to infinity 1 over t, which is 0. And this is less than or equal to. Now, on the right-hand side, we will assume, for example, that m is equal to square root t. So we will change m with t. We change m with t, and in such a way that m over t will tend to 0 as t tends to infinity. Okay. So if we do this particular choice, then the right-hand side becomes limsup as t tends to infinity of the remaining term will be 1 over expected value of u tilde. Note now that basically we still have the limit. U tilde now is not a constant with respect to the variable t. Let's remind ourselves, the modified renewal process, u tilde is defined in terms of u given this m. So if we make m a function of time, then u tilde will basically its distribution will depend on t. Okay, so that's the reason here. I will have limit suprema. I will leave it. This is in the original process, 1 over the expected value of u is a given constant, but now this depends on m, and so it depends on t. Note something, okay, and this is very important, that u tilde is less than or equal to u with probability 1. This is very important to note now. The reason is that both are equal if u is less than or equal to big M, but u tilde is M, which is strictly than u if u exceeds M. So it's always the case that u tilde is less than or equal to u. So this means that expected value of u tilde is upper bounded by the expected value of u. If by assumption we are assuming that this is finite, then this is also finite. Now, let's note something. What if we examine both systems at this time instant here? So let's say that this is t. The number of arrivals, so n of t is equal to 1, 2, 3, and tilde of t is 1, 2, 3, 4. And it is general that n of t is less than or equal to n tilde of t. At any time instant t, n of t must be less than or equal to n tilde of t. And this is due to the way we have constructed the modified renewal process. In the renewal process, the interarrival time is less than or equal to the original interarrival time with probability 1. In the modified renewal process, whenever the interarrival time exceeds big M, then u tilde is equal to big M itself. And so let's say that the points will get more crowded in the modified process. So n of t will be less than or equal to n tilde of t. And if we take expectations, small m of t is less than or equal to m tilde of t. So using this, we can go back to our result and say that m of t is less than or equal to m tilde of t. So you can divide by t and take limit supremum. So limsup t tends to infinity, m of t over t is less than or equal to limsup as t tends to infinity, m tilde of t over t, and this is less than or equal to limsup as t tends to infinity, 1 over the expected value of u tilde. Okay, we are done. Remember, I mean, our game plan. The game plan is, after proving this, is to show that limit supremum of t as t tends to infinity of small m of t over t is upper bounded by 1 over the first moment of the inter-arrival time of the original process. Now, we are very close, but we are not there yet, because what we have here is not 1 over the expected value of u, unless we demonstrate that basically this limit supremum as t tends to infinity of 1 over the expected value of u tilde is exactly 1 over the expected value of u. So if this is equal to 1 over the expected value of u, we are done. We are done, because in this case, limit infimum as t tends to infinity of m of t over t will be equal to limit supremum as t tends to infinity of m of t equal to t. And so the limit exists because these two guys are the same, and we have a limit, and this limit will be 1 over the first moment of the inter-arrival time. So the last step is limit supremum t tends to infinity, expectation of u tilde is expectation of u. What is the expected value of u tilde? So don't forget that u tilde is u if u is less than or equal to m, and it's m if u is greater than m, and we chose m to be a function that if you divide by t, it will go to 0 as t tends to infinity. We took it to be square root t. So here the limit will be, let's write down an expression for the expected value of u tilde. So expectation of u tilde is expectation of u, indicator that u less than or equal to m, plus expectation of m, indicator that u is greater than m. Now, as t tends to infinity, m itself will also tend to infinity, and both expectations have a limit as m tends to infinity. For this one, here this is upper bounded by u, and expected value of u is finite. So by the dominated convergence theorem, we can take the limit, okay, the limit of indicator as u less than or equal to infinity, and this will be 1. So this will, by dominated convergence theorem, this will converge to the expected value of u. So hopefully this will converge to 0. This is upper bounded by expectation of u, indicator u greater than m, and this is upper bounded by u, and this expectation of u is finite. So by dct, this is expectation of limit as m tends to infinity of u, indicator u greater than m, and this will be equal to 0.